So we're going to start the second lecture on the Chebotarev density theorem. So I want to start by reviewing what Frobenius elements are and give an example of a calculation related to them for a non-abelian Galois extension to kind of see roughly what things can look like. And then I'll kind of sketch the ideas that go into trying to prove the Chebotarev density theorem. To start, are there any questions about stuff from last time? I don't see any hands coming up. So, okay. So let me first recall how Frobenius elements are described, and then we'll do a calculation for them. So we have a Galois extension, then oh yes. Yes. So the question is about splitting of primes, and when I talk about applications of the Chebotarev density theorem, then you'll see one of the consequences is the property of splitting of primes. Yep. And I should say some of the consequences that I present of the Chebotarev density theorem later were in fact things that were proved before the theorem, and now we think about them as consequences, but they kind of historically came before. So like the theorem that was referred to in the question about splitting of primes, if I understand the question correctly as what I'm thinking, that result was actually known before Chebotarev, but now we absorb it in as a special case. So we have a Galois extension of Q, and we have a prime number P, and we have a prime ideal that divides P in the ring of integers of OK, like maybe it's the ideal driven by 1 plus 2i divides 5 in Z bracket I, for example. So if we let G be the Galois group of K over Q, then this acts on the prime ideals dividing P, or as we say, lying over P. And it does so with exactly one orbit. You can get from one such prime to every other such prime by hitting it on some elements in the Galois group. So if we have all the different prime ideals that divide P, then we can find elements in the Galois group that move them around, and we can get from anywhere to anywhere else. Yeah. Okay, it's not at all obvious. I mean, the example that I think I may have mentioned last time, right? If you take Q adjoint I over Q, and we have like the prime 5, its factors are 1 plus 2i and 1 minus 2i, and those are complex conjugates. And using complex conjugation, you can go from one to the other, and that is one of the elements in the Galois group of Q adjoint I over Q. So if you use complex conjugation. So just to illustrate the idea, so you can get from anywhere to anywhere among the prime ideals dividing a particular prime, and so the main result that led to what a Frobenius element is that if you take a prime ideal upstairs in OK, there's always going to be an element in the big Galois group of K over Q with a property that it looks like the little Pth power map. It looks like raising to the Pth power. So on the field OK mod P, we have the fact that this element appears to behave like the little Pth power map. And so there could be more than one of these for a particular prime ideal, but for almost all but finitely many prime ideals upstairs, this element in the Galois group is unique. For those who've had enough algebraic number theory, it's for the unramified prime ideals. But in any case, for all but finitely many, there's only one, and then we call it the Frobenius element. And there are all kinds of notations people might write, which can range from the reasonable to the strange. whatever that means. I mean, whatever the notation means, not whatever the word strange means. So anyway, so all kinds of, so I'm just going to write things like that, and we call this the Frobenius element at the prime ideal. So a finite number of times it's ambiguous, and so we don't make a definition there, but almost all the time there's one such thing. Now, if you try to make sense of this for different prime ideals that divide the same prime number, you might get different elements, but they're all conjugate to each other. So as you vary the prime ideal upstairs, then what happens is that all the different Frobenius elements are conjugate, and so these things, in fact, fill up a conjugacy class in the group. So what we can say then is that we can associate to a prime number what I'll call Frobenius sub little p, the collection of Frobenius elements at the prime ideals dividing p, and this is a conjugacy class in the group called the Frobenius conjugate class of the prime number. So for a few times it might be ambiguous, so it's only defined for all but finitely many primes. All right, so this is the generalization of reducing a prime number mod m. Right, you can reduce a prime number mod m and get a unit mod m for all but finitely many prime numbers. That's in Dirichlet's theorem. And so now, in general, for a Galois extension, you can turn a prime number into a conjugacy class in the Galois group, except at a finite number of primes, there's some problems, so we kind of ignore those. And so this is a kind of a very non-obvious procedure. You take a prime number, then you go to the ring of integers of the Galois extension, you pick a prime ideal dividing that prime number, and then you find the element in the Galois group that modulo that prime ideal looks like the Pth power map everywhere for that prime number you started with, and then you vary the prime ideal dividing the prime number, and that gives you conjugate elements. So that's how you go from a prime number, for all but finitely many of them, to a conjugacy class. All right. So this gives us Frobenius elements for prime ideals upstairs, Frobenius conjugacy classes for prime numbers downstairs. So let's take a look at an example. Are there any questions? No? All right. So let's do an example where the Galois group is non-abelian. So we get some interesting conjugacy classes, because if I had an abelian Galois group, then conjugate classes are the same as elements. So you really are actually going from prime numbers to elements in the Galois group. But if it's non-abelian, well, you might have to settle for conjugacy classes. Okay, so this is a Galois extension of Q of degree 8. The Galois group here is it's isomorphic to the dihedral group of order 8. Whether you want to call that D4 or D8, that's up to you. And so what I would like to do is let's take a prime ideal in the ring of integers that divides the prime number 5. You might think the ring of integers is Z bracket, the fourth root of 2 and I, and that's not true. It's a little bit bigger than that, but we're not going to worry about it. So take a prime ideal that divides the number 5, and I should say here, so if we write G for the Galois group, the elements in G, each element in G is determined by its values on the 4 different fourth roots of 2. I mean, you could say the fourth root of 2 and I separately, but I just want to list out the 4 different fourth roots of 2. And if I call this like 1, let's do them in the order of powers of I. So 1 I fourth root of 2 minus the fourth root of 2 minus I fourth root of 2. So if we call this 1, 2, 3, and 4, any permutation of these 4 fourth roots of 2 can be thought of as maybe a more familiar kind of permutation on 4 symbols, on the numbers 1 to 4, if we want to write it as a permutation. So, okay, so let's try to figure out what is the Frobenius element at a prime ideal, dividing the number 5. So this is, we somehow have to use this property. So the idea is that the ring of integers mod p is some finite field that's going to contain the integers mod 5, and so we want to kind of take advantage of that. So so what we know by the definition is that this is some element, mysterious right now, that's going to look like raising to the 5th power everywhere. And even though I don't know the whole ring of integers, I can at least say, well, the 4th root of 2 is going to look like the 4th root of 2 to the 5th. And, well, that's twice the 4th root of 2. And the value on I is going to be congruent to I to the 5th. And I to the 5th, well, that's just I. Now, here's the thing. OK mod p is a field of characteristic 5. Plus and minus I are different, right? The polynomials x to the 4th minus 2 and x squared plus 1 mod 5, these are separable polynomials. They don't have multiple roots in characteristic 5. So we know that they're going to factor because they already factor in OK with the roots, the 4th roots of 2 and the plus or minus I. And so when you reduce the factorization, it's going to split into linear parts, but we know it's separable. So the different 4th roots of 2 and OK mod p have to stay different because they're going to show up as roots of the separable polynomial. Plus or minus I are different. So since I and minus I are not the same, then from the fact that sigma I is I mod p and minus I is not the same as I means the congruence forces equality. It's just like minus 1. If you have a number that's plus or minus 1, and I know it's congruent to 1 mod 4, it must be 1. Right? There's no choice in the matter. If I said an integer is 1 mod 4, ooh, what is it? But we can distinguish those, and so there's some information. Now, the 4th root of 2, well, I know that twice the 4th root of 2 is definitely not plus or minus the 4th root of 2 mod p, because the 4th root of 2 is not 0 in characteristic 5, and so I could cancel 2 is not plus or minus 1 mod 5 in characteristic 5. So 2 4th root of 2 is not plus or minus the 4th root of 2. And so therefore that tells me that this number has to be congruent to plus or minus I 4th root of 2. Because it's going to be, since we have sigma the 4th root of 2 is twice the 4th root of 2, that's some 4th root of 2, and 2 to the 4th is 1 mod 5. Everything's consistent. So, and that is not plus or minus the 4th root of 2, and so therefore at least we know sigma 4th root of 2 has to be plus or minus I, not plus or minus the 4th root of 2. It's plus or minus I 4th root of 2. So there's some information. So, whoops, sorry about that. So sigma 4th root of 2, we'll just write it down again, is that, and sigma of I is definitely I. So we have two options here. If we write out our 4th roots of 2 in order by powers of I, and then we have our sigma alpha. So maybe the value with the 4th root of 2 is I 4th root of 2, or maybe it's minus I 4th root of 2. Let's see what happens. Well, if 4th root of 2 goes to I 4th root of 2, and I is fixed, then I 4th root of 2 in the second column is going to go to I times I 4th root of 2. That's minus the 4th root of 2. And minus 4th root of 2 is going to go to the negative of the first thing. And minus I 4th root of 2 goes to the negative of what I 4th root of 2 goes to. So there we go. In the second case, if 4th root of 2 goes to minus I 4th root of 2, then I 4th root of 2, sigma multiplicative, I is fixed, goes to I times what we just found. So I times minus I is 1. So that's 4th root of 2. minus goes to the negative of the first thing, and minus I times that goes to the negative of the second thing. Okay, so what permutations are these of the four? Let's copy this sucker. So if we make a little reminder here, okay, so if we use this notational simplification, then the first row, 4 through 2 is 1, and 1 goes to I 4 through 2, which is 2. I 4 through 2 goes to minus 4 through 2, which is 3. And minus 4 through 2 goes to minus I 4 through 2, which is 4. So we get the 4 cycle 1, 2, 3, 4. The second row, 4 through 2 goes to minus I 4 through 2. Well, that's the last element, so that's 1 goes to 4. Then minus I 4 through 2 go to the end of the table, goes to minus 4 through 2, which is 3. And then minus 4 through 2 in the third column of the table in the second row goes to I 4 through, which is 2, and it goes back to 1. So if you don't know which one it's supposed to be, at this point, you know it's one of those options, and you know what? Those are conjugate. These are conjugate in the dihedral group. There are 2 4 cycles in the dihedral group, and these are actually conjugate. So we don't care about, I never even knew what the prime ideal was. I just knew it divided 5. And we wound up with one possible conjugate class, and it has to work. And so therefore, we've determined that the Frobenius conjugacy class, this one is, well, I'm going to write it as 1, 2, 3, 4, and 1, 4, 3, 2 with that notation for the 4th roots of 2. Or we could say, excuse me. I'm sorry. That was not correct. I should have said, it's this or this, depending on the prime ideal. And so the Frobenius conjugacy class associated to 5 is the set consisting of these 2 permutations of the roots that are elements in the Galois group. And so you get a single conjugacy class in the Galois group. So we turned the prime number 5 into a conjugacy class of the Galois group. And this same thing works for any prime except for 2. At 2, you have some ambiguity. And so you have a Frobenius conjugacy class for every odd prime. All right. And so just as a remark, for the cyclotomic fields, where elements in the Galois group always send primitive mth roots of unity to powers of primitive mth roots of unity, where the exponent is relatively prime to m because it has to still have order m. For primes that don't divide m, the Frobenius elements, because this is an abelian Galois group, the units mod m, it is literally just the congruence class of p mod m in z mod m star. For all but finite many primes, you get a distinguished element because the Galois group here is abelian. So conjugacy classes are individual elements. Okay. So let's recall what the let's switch to green now. So let's now recall the statement of the Chebotarev density theorem. For Galois extensions of Q. And what we're going to, let's just make a little bit of notation here. So if I have a Galois extension and a conjugacy class, call it capital C for some reason, then let's count. I'll write pi sub c of x for the set of primes, the size of the set of primes up to x, whose Frobenius conjugacy class is this chosen one. So for a few primes, this won't make any sense, but don't worry about it, right? And actually, for comparison, another important counting function, pi sub k of x, is a number of prime ideals of norm up to x. That means the size of the field OK mod p is at most x. So there are 2 important results. There's the prime ideal theorem, which is the number field analog of the prime number theorem. So this goes back to Landau. I think only like less than 10 years after the prime number theorem was proved. So anybody remember that? What's the statement of the prime number theorem? Yeah. X over natural log of x. So the prime ideal theorem, you might think maybe it'll look like that, but it'll have some funny constants. No, it's exactly the same asymptotic statement. The number of prime ideals of norm up to x grows like x over natural log of x. The ratio goes to 1. It's exactly the same expression asymptotically, and the Chebotarev density theorem says that for each conjugacy class, this grows proportional to x over log x, but there's a coefficient, the size of the conjugate class over the size of the group. So if anyone has a t-shirt for the summer school, you'll find this last asymptotic relation written on your shirt. Okay, practical application of the Chebotarev density theorem. So don't say it doesn't have any applications to real life. Okay. Well, we can pretend that they do for the purpose of this talk. So just to simplify, without loss of generality. All right. So in particular, if the Galois group is an abelian group, conjugacy classes have size 1. Conjugate classes are individual elements, and the Chebotarev density theorem is saying that if you count the prime numbers whose, well, now Frobenius element is this individual thing. Remember, it's going to make sense for all the finitely many primes, and divide by the number of primes up to x, which grows like x over log x. Then this is asymptotic to, 1 over the size of the group, the reciprocal of the size of the group. Every element has its equal proportion of primes that have it as its Frobenius element, if the Galois group is abelian. And in the special case of a cyclotomic field, this exactly becomes Dirichlet's theorem on primes and arithmetic progression, since Frobenius elements are just p mod m, and 1 over g is 1 over phi of m. So it is an exact generalization. Okay. Now, in order to prove the Chebotarev density theorem, well, okay, so Chebotarev himself formulated it exactly in the context that I've been discussing it, just for Galois extensions of Q. But you can generalize the formulation for Galois extensions of number fields that don't have to have the base field being Q. Someone asked about this last time. So it turns out that I'm going to phrase the Chebotarev density theorem for Frobenius elements, Frobenius conjugate classes, to allow a more general base field than just the rational numbers. And that more general formulation actually leads to a simplification in the proof. So we're going to generalize the statement and take advantage of that. So let's see what a more general version of the theorem looks like. We're going to allow a base field not necessarily being Q. Maybe the base field could be Q adjoin the square root of 2, or Q adjoin I, something like that. So instead of Galois extensions of Q, we'll take a number field F. Maybe it's the rationals, but maybe not. And we'll take another number field. It's a Galois extension of F. So, so in here we have ring of integers. In here we have ring of integers. And now, because we have a general ring of integers downstairs, we're going to write our general prime with the same letter that we used for the prime upstairs when we were working over Q. And so then we need a new letter for the prime ideal upstairs. And so then we can use a capital P. Maybe you just want to write a Q instead. Maybe you'd be happier with that, but we'll stick to this. I put in the time to try to figure out how to write these, so I'll do it any chance I can get. Oh my God, I first thought it was, of course, the letter B. It took years for me to get over that. Maybe I shouldn't have said that. Anyway, so what's the analog of a prime number now is a prime ideal downstairs. And so the thing to realize is instead of prime numbers for counting purposes, now the base field has some size, the norm of the prime ideal downstairs. This is the replacement for the size of Z mod P. And so the extension of residue fields OE mod its prime ideal contains OF mod its prime ideal. So in this up here on the left side, this ideal is a factor of the extension of the prime downstairs to an ideal upstairs, just like previously the prime ideal upstairs is a factor of POK. And so, so the residue field at the ideal upstairs extends the residue field at the ideal downstairs. And Galois theory of finite fields says that the Galois group, they're always Galois extensions, and the Galois group is iterations of the Qth power map, where Q is the size of the field downstairs. And so OE mod big P as an extension of OF mod little p is Galois, and the group is generated by raising to the norm Pth power. And so the fact is that some elements in the Galois group of number fields satisfies the condition that it's going to look like the norm little Pth power map for all elements upstairs. This is the exact analog of looking like the little Pth power map when the base field was the rational numbers. And moreover, this sigma is unique for all but finitely many primes upstairs. And so this is called the Frobenius element. Sigma is the, when that happens, when there's only one choice, this is the Frobenius element at the prime upstairs. So we might write it as Frobenius element for this field extension. And if we think about it in terms of the prime ideal downstairs, as you vary the prime ideal dividing it upstairs, you get, as the Frobenius elements vary over the same prime ideal downstairs, you get conjugate elements. Get conjugacy class. And so that's what the Frobenius element at little p downstairs means, is the collection of Frobenius elements, actual elements of the prime ideals dividing it upstairs. And that's just going to be a full conjugacy class upstairs, except that a finite number of primes with some ambiguity, and we don't worry about it. Okay, and so now we can formulate the Chebotarev density theorem for this extension. So this is the Chebotarev density theorem in this setting, and it would say, if you gave me a conjugacy class in this Galois group of number fields, that if you count for large X, the number of prime ideals downstairs whose norm is up to X and whose Frobenius conjugacy class is the chosen one, and you divide by the number of prime ideals downstairs whose norm goes up to X, that this has a limit, the size of the conjugate class over the size of the group. So it looks just like the same statement, except the bottom is no longer the integers in the rational numbers with prime numbers, but we're working with ideals. Okay. Are there any questions? Yes.
Small factor P of some extension.
Well, I'm writing the number field extension E over F. Yeah. So when we're working with a base field F that's not Q, I'll write, I think it'll be clear from context.
Okay, awesome.
Okay? Yeah. So how do we prove the Chebotarev density theorem? Let's switch colors. What should we use next? Pink? Let's use pink. Okay, so we have 20 minutes. Fasten your seatbelts. All right, so big picture, there are two steps. Step one is start, step two is end. So the first step is a reduction step. So this step, well, let me tell you what the steps are, and I'll make some comments on it. So what we're going to do is we're going to reduce the general theorem that I just stated to the case when the Galois group is abelian. In fact, the reduction is even going to lead us to reduce to the case when it's just cyclic, but I'll just phrase it this way: reduce to the case when the Galois group is abelian, and in doing so, I'll say it's at the cost of increasing the base field. So the process of trying to prove this general theorem, we're going to replace F with a field in between E and F, and as a result, the smaller Galois group of E over that intermediate thing will be abelian, and the general case can kind of be reduced to that case depending on the conjugacy class. And then, of course, the next step is to prove the theorem if the Galois group is abelian. Now, or in fact, if it's cyclic, but that distinction is not going to materially affect the argument. So this is not an approach that Chebotarev could have taken. For him, it was only a theorem about Galois extensions of Q. He did not have a formulation. He did not prove a result with a general base field. And so this whole approach, this came up by Düring about 12 years after Chebotarev's version. But this is the one that's presented nowadays. It fits in with other themes and a number of things. You're trying to develop everything where you allow a general base field, not just the rational numbers. So I want to kind of sketch how these two steps go. So how do you reduce yourself to the case of a cyclic extension? If your Galois group is not already cyclic, maybe it's highly non-abelian, how do you reduce to the case of an abelian or in fact cyclic extension? So what the idea is that you pick some elements in your conjugacy class. So we're in a general setting here, the general Galois group, and then what you do is we're going to use Galois theory. Between E and F, you have the subfield, I'll write E tau, the elements that are fixed by tau. You know, you pick an element in a conjugate class, everything else is conjugate to it. Just you take one element, just go with it, and you get an intermediate field. So the elements that are fixed by this choice of tau, they might not be fixed by conjugates of tau. And so in the Galois correspondence, the subgroup that fixes the things that tau fixes are just the powers of tau. It's the power of Galois theory. And the nice thing here is that, so we have a new intermediate field. I'm going to call it F prime, because it's going to play the role of a new base field. And this Galois extension is cyclic. It's just the powers of tau. You take the fixed field of tau, its subgroup that fixes it are the powers of tau. E is Galois over that intermediate field, and the Galois group of E over that is exactly the powers of tau. And so what we're going to argue is that the Chebotarev density theorem, Chebotarev for the conjugate class C in this Galois group, this kind of general case, is equivalent to the Chebotarev density theorem for this individual element in this cyclic Galois extension. If you change to a different element in the conjugate class, there might be a different fixed field, and so you might have a different cyclic replacement group. So the statement of Chebotarev for the conjugate class in that Galois group is equivalent to the statement of Chebotarev for this individual element in this cyclic Galois group. Okay, and so why does that work? So the idea is that we're going to look at two sets of primes. So if we consider the prime ideals downstairs, whose Frobenius conjugacy class is the one we're interested in, and let's consider the primes q. See, I'm going to use the letter frac q in the ring of integers of f prime, the intermediate field. Now that, as a subfield of E, has E as a cyclic abelian Galois extension, so we get individual Frobenius elements there most of the time. I'll say equal to tau. Okay, so we, on the left side, prime ideals downstairs, whose Frobenius conjugacy class in the big Galois group is the chosen one. And then we have prime ideals in the intermediate ring of integers, whose Frobenius element in the cyclic Galois group generated by tau is, in fact, the element tau itself. So it turns out that that there's a way to go back and forth between prime ideals in F and prime ideals in F prime. I mean, the ring of integers in F and F prime. There is a correspondence between these sets of prime ideals off a subset of density 0. So all those limits I was taking, something divided by the number of prime ideals, if you kind of, like a finite set of primes, if you take it in or out of these numerators, you're not going to affect the limit. If it already existed and you take out a finite set, it won't have an effect. So you call a set of primes of density 0. If when you count those in the numerator, then the limit would be 0. And so if you adjust sets of prime ideals, there could be infinite sets of density 0. So we're going to ignore a set of density 0 for what I'm about to say, but I see a hand raised. I'm not going to care about error terms for today. I just want to sketch the idea of the asymptotic statement. And the issue of error terms for applications is important. And so I will be prepared for that next time or in the last lecture. So right now, we just want to kind of explain what's happening in the, just for the basic asymptotic statement. So there's a way to go from prime ideals downstairs to prime ideals in the middle with these subject to these conditions. And it turns out that there's a correspondence between them. Away from subsets of density 0, you can you get a correspondence where corresponding prime ideals have exactly the same norm. So your count of in each set away from subsets of density 0 is going to be the same, and the number of Q's upstairs that correspond to a given P turns out to equal the integer. So we did a little bit of group theory here. The centralizer of tau in the big Galois group over the powers of tau. So remember, the centralizer of an element in a group is the elements that commute with it. And that contains the powers of the element itself. So that ratio is, in fact, an integer. The size of the subgroup generated by tau is, in fact, the degree of E over F prime from Galois theory. If you look at the diagram of fields, the size of the subgroup of tau. So I can change this. And so, whoops. And so, because the prime ideals in this correspondence is like a many-to-one mapping, where this kind of many count is basically always the same off subsets of density 0. And so what that then tells us is that the if we take this limit for the count of the Q's, with Frobenius element tau, I'm just going to write the size of the number of Q's of norm up to X. that this is going to equal up to the factor, up to this multiplicity factor, the limit with the count of the p's. Norm p up to x, Frobenius p is c, divided by count of prime ideals downstairs up to x. And so we get this extra multiplying factor, and I say that these limits are equal if either one exists. Well, so if we already knew the Chebotarev density theorem, if it's proved for abelian, hence cyclic Galois extensions of number fields, then that means that the left-hand side is actually equal to 1 over the degree of the extension. That's 1 over the number of powers of tau. And so that makes the left-hand side equal to the right-hand side. And so then on the right-hand side, we just copy this and bring it down. Okay. Can you do that with your paper? All right. So then we just get to cancel the terms. And so therefore, we see that the limit of the number of primes up in the original thing we care about, counting primes of the given Frobenius conjugacy class, divided by the number of prime ideals overall downstairs with norm up to x. This is 1 over the centralizer of tau, but we didn't want that. We wanted something else. Well, from group theory, if you want to count the size of a conjugacy class, the size of the conjugate class of an element, what's that equal to? It's the size of the group divided by the size of the centralizer. That's some theorem from group theory. And so therefore, 1 over the size of the centralizer is, in fact, exactly what we were hoping for. Okay, so we've reduced the general problem. I never went into the details of this, whoops, right? This whole thing here, there's a correspondence that's kind of many to one that preserves the norm. I mean, this one involves some explanation, but it's the basic idea is there's a way of passing to an intermediate field, and you can reduce the general case to that, which has a cyclic Galois group. Okay. So now we have to discuss how do you prove the Chebotarev density theorem in the case of an abelian, or really cyclic is all we care about. So we had step 1. That was a sketch of step 1, and now we have a sketch of step 2. So now we have an abelian. I really only care about the cyclic case, but I'm going to phrase it in the abelian case because there's really nothing gained by just focusing on cyclic groups. But being abelian is definitely helpful. So we have an abelian Galois extension, and I want to prove the Chebotarev density theorem in that case. So there's our abelian Galois extension. I take a prime downstairs, and I take a prime. Oh, terrible. Let's try that again. Good enough. All right. So so I want to pick an individual element, right? So we pick an individual element in this group, and we want to prove the Chebotarev density theorem for counting the P where the Frobenius element is that thing. Conjugate classes are individual elements since we're in an abelian Galois group. So I want to avoid the prime ideals that don't have this make any sense, where the Frobenius construction doesn't make any sense. So there's only a finite number of such primes. They're the ramified primes, but we don't have to worry about that. So let M be, let's make an ideal built out of the primes that we want to avoid. Let's take the product of P where their Frobenius construction makes no sense, where it's not well defined. Okay, so just multiply those together. So that's some ideal whose prime factors are the ones we want to avoid. And so let's look at the ideals that are relatively prime to M. So we can factor into prime ideals. So you want to take the ones that are relatively prime to M. You want to look at the ideals that don't have a prime factor where the Frobenius is not defined. And so then this is not a group, but it's a set of ideals closed under multiplication. Think about like in the integers, think about like the odd numbers, right? The integer is relatively prime to 2. That's closed under multiplication. It's not a group, but it's closed under multiplication, has an identity. And so we can turn ideals in here into elements in the Galois group because these consist of products of primes where the Frobenius construction makes sense. I can get a mapping from all of these ideals to the Galois group by sending primes that don't divide M to their Frobenius elements. It's kind of like circular. We've defined an ideal built out of the primes where it doesn't make sense. So the primes that don't divide it are the ones where the Frobenius makes sense. And then just extend by multiplicativity. Extend to all ideals relatively prime to M by multiplicativity. If you've ever heard of the Jacobi symbol, this is exactly like the passage from the Legendre symbol to the Jacobi symbol. You spend a lot of time defining the Legendre symbol and its properties, and then you just define the Jacobi symbol to just multiply the Legendre values based on the factors of the term in the Legendre symbol and the Jacobi symbol. So it's kind of like that. So this is a kind of very formal definition, extend a function. I'm not saying a Frobenius of a non-prime ideal. I'm just going to define this. So this is what somebody was asking yesterday about the Artin mapping, is what this thing is. So it turns out, hard fact, is this is surjective. Every element in the Galois group arises as a value of this multiplicative mapping. Okay, the truth is it's actually a value at a prime ideal, but that's the Chebotarev density theorem, so it's kind of a circular argument. So you can show first that this is a surjective mapping. This is very non-trivial, needs a lot of background, but one can appreciate the statement of it. Okay, somehow you can show that the value are everything. All right, so if we let H be the A's that are mapped to the identity element in the Galois group. So I'm going to kind of treat this almost like it's a group. I mean, there aren't really inverses, but so it's not really a kernel. It's not a group homomorphism, but you can make sense of these kinds of things. So you quotient out, you identify things that go to the same thing, and you can actually build a group out of that. And so you get an isomorphism. Okay, it's almost like dealing with groups. And so this is some finite group. This is some finite abelian group. Okay, and so the left-hand side is sort of like the units mod M. The right-hand side is kind of like the Galois group of a cyclotomic field. So kind of like a Galois group being isomorphic to a more concrete group. And so if we let some coset on the left correspond under this isomorphism to the element of interest on the right, the sigma, then counting the primes whose Frobenius element is the automorphism of interest, it's the same thing as counting on the left side primes that are in the same coset as, that are in the coset that corresponds to the sigma. And so now what we want to do is the Chebotarev density theorem is turned into the statement that I want to show that the limit, when I count primes with norm up to x that are relatively prime to m, that are congruent to b mod h, divided by the set of count of all primes with norm up to x, I would like to show that this is 1 over the degree of the extension, the size of the Galois group. But because our Galois group was isomorphic to that kind of group of ideals, so to speak, this is 1 over the size of Im mod h. And if you look at this statement, what does this resemble? Anything that we talked about before? Vaguely? I'm not stating, there's no Frobenius elements in it anymore. What does it resemble? Yeah? Yeah! This looks just like Dirichlet's theorem, and it's proved in the same way. So this is proved in the same way as Dirichlet's theorem. So if you've ever seen a proof of Dirichlet's theorem using L functions of characters of the group of units mod m, you take characters of this Im mod h, that's a finite abelian group, and develop L functions and their properties, and the same arguments go through. It's more technical, but it's the same basic idea. And so in this way, you reduce the cyclic case or the abelian case to the same approach used for Dirichlet's theorem. Okay? And so we're 2 minutes over, so this is a good place to stop. Yeah, that's it. Other questions? Questions? Yes?